Good afternoon. Welcome to week 3 of the course of the NPTEL course on coherence and quantum entanglement. So this is week 3, and in this week we have been introduced the Mach-Zehnder interferometer, and in particular we have looked at the temporal interference effects and how to quantify coherence in the temporal domain. So here in this week we will be looking at questions wherein we have to find out the degree of coherence and the coherence time for the temporal domain. So let us begin with the very first question. Let me read out the question first for all of you. So this is problem 1. Suppose the cross-spectral density function of a field is given by W omega 1 comma omega 2 equals S omega 1 delta omega 1 minus omega 2, where the expression for SW is given as follows. It's a Gaussian distribution, and omega naught is much larger than delta omega. That means the width delta omega is much smaller than the peak location omega naught. Now for this particular expression for the cross-spectral density function, we are supposed to evaluate the intensity of the field, and we are also supposed to evaluate the coherence time of the given field. So take about a few minutes to read the question again and to understand exactly what we are supposed to do. Try to write down the first few steps that would be essential in solving this problem. After that, I will discuss the solution with all of you. As I always say, it is a good idea to start solving the question before the instructor solves it for you. That way you will gain some problem solving practice, which will be beneficial for you when you attempt the quiz problems and the exam problems. That way you will be able to build confidence and you will understand how to approach a problem. Otherwise, if you just wait for me to solve it and then copy it, that may not be as beneficial. So take about a few minutes just to think and visualize. Okay, so now that you would have spent a few minutes, let me start solving the question. Okay, I need to get my pen. Let us look at part A. We need to find out the intensity of the field. But before that, let us look at the properties of this field that we have been given. So because the expression for the cross-spectral density function W is as follows, wherein there is this delta function over here. Because of the presence of this delta function, this field is a stationary, represents a basically stationary random process. So that means that the field is stationary. And what does stationary mean? That it is time independent. What is time independent? All the correlation functions, the mean, the intensity, all these quantities are time independent. This also means that there is absolutely no correlation between different frequency components. And also because the expression for S omega is like this, that means this is a Gaussian spectrum. It's a Gaussian spectrum for the field. And because delta omega is very small, that means the field is quasi monochromatic. Quasi monochromatic means that it is very nearly monochromatic. That means that the spectral width is very small, so much of the intensity is contributed by a single frequency omega naught, and there is a very narrow spread of frequencies around that central frequency omega naught. So that is what quasi monochromatic means. Now let me write down the expression for intensity. I'm just writing down the expressions. So the intensity can be given by gamma, where both the time arguments are the same. Now for a stationary process, the cross correlation function for a stationary process, the cross correlation function gamma is independent of time. So this just boils down to gamma of tau. Tau is the time difference. Now, from the Wiener-Khinchin theorem basically relates the cross correlation function with the cross spectral density function, or in this case gamma tau with S omega. So let me write down the Wiener-Khinchin theorem. So this is the Wiener-Khinchin theorem, which relates S omega with gamma of tau. Now we can plug in the expression for S omega, which is given to us, which is the Gaussian spectrum. Now let us simplify this. The constant term comes out of the integral. And let me make a substitution. Let omega minus omega naught be equal to omega prime. So this means d omega equals d omega prime. Let us make this substitution. Let me make another substitution. Let alpha be equals to 1 over 2 delta omega squared So this is minus alpha omega prime squared exponential minus I omega prime tau d omega prime. Now I will use the method of completing the whole squares in the integrand. So this will give me, the integrand becomes so this becomes my integrand upon completing the whole squares. You can easily check this by expanding. So expanding would give me basically minus alpha, and then I would have omega prime squared minus tau squared over 4 alpha squared plus I omega prime tau over alpha and then the other term from the other exponential, that is minus tau squared over 4 alpha. Now if I combine everything, this gives me minus alpha omega prime squared, then minus minus becomes plus, 1 alpha cancels out, so this becomes plus tau squared over 4 alpha, then again 1 alpha cancels, and minus I omega prime tau, and then minus tau squared over 4 alpha, so this term cancels out, giving me minus alpha omega prime squared minus I omega prime tau, which is exactly what my initial integrand was. So this was just completing the whole squares. Now I'll simplify further. Now I can make another substitution. I can say omega prime plus I tau over 2 alpha equals omega double prime, and this gives me d omega prime equals d omega double prime. Now from the integral of the Gaussian, we know that integral exponential minus alpha x squared is from minus infinity to infinity is root pi over alpha. So using that, I will get the following. And let me substitute back the value for alpha, which is 1 over 2 delta omega squared. And then this root pi over alpha will cancel with this root 2 pi delta omega, because alpha is 1 over 2 delta omega squared. So let me call this equation 1. Now let us write down the degree of coherence. Because it is stationary, it is time independent. I need to now find out these intensities in the denominator. So let me write down. This is nothing but cross correlation function with the same arguments. Sorry, not t1 t2, t1 t1. Which is simply integral of s omega d omega Now I will use the same substitution, that is omega minus omega naught equals omega prime. And d omega is equal to d omega prime. And also let us put alpha equals to 1 over 2 delta omega squared. This is because of the Gaussian integral. And alpha is 1 over 2 delta omega squared, so that cancels out, giving us 1. Therefore, the degree of coherence function is given as follows. And this gives me that the argument of gamma is omega naught tau. Therefore, we have the expression for the final intensity. And this we can see is clearly independent of time and depends only on tau. Tau is here and tau is also independent of time and only depends on tau, which is the time difference. So that was for part A. Part A, in which we were supposed to evaluate the intensity IT of the field. Part B asks us to evaluate the coherence time of the field. So coherence time is nothing but the width of the degree of coherence function. Now clearly the width of this function is 1 over delta omega, which is the coherence time. And how we come at this conclusion, that is because the width of a Gaussian function is given as follows. If we have a Gaussian exponential minus x squared by 2 sigma squared, then the width is sigma, which is also the standard deviation. So this completes problem 1. We were given an expression for the cross-spectral density function W. This expression had delta function in its expression, so it was stationary, and the expression for S omega, the spectral content was quasi-monochromatic Gaussian spectrum, and we were supposed to evaluate both the intensity and the coherence time for the given field, which we have done. We made use of the Wiener-Khinchin theorem to calculate the intensity, or to calculate the cross correlation function, and from the cross correlation function we find out the intensity and the degree of coherence functions. So that was for problem 1. Take about a few minutes to recapitulate what we have done and to understand the entire process. Then we will proceed to the next question. On the way, we have made like a few substitutions to evaluate the integrals, which are pretty standard substitutions used to find out integrals involving Gaussian functions. Also, we made use of this completing the whole squares technique, which is also pretty standard. And this Gaussian integral is one such expression which you should remember always. It comes in very handy. Yeah, so just take a moment before we move ahead. Okay, so now let us proceed to problem number 2. There are 5 parts in this problem. Let me read out the question first. Consider a field Vt given by Vt equals a exponential minus I omega t plus b exponential minus I omega bt, where omega a and omega b are two frequencies and a and b are two real numbers. The parts are: part A, find out the cross-spectral density function W omega 1 omega 2 of the field. Part B, find out the intensity IT of the field. Part C, find out the cross correlation function gamma T1 T2 of the field. Part B, is this field stationary at least in the wide sense? Part E, find out the degree of coherence function of this field. Again, take a few minutes to read this question once again and to understand what exactly the question is asking us to do, and try to write down a few steps for at least the first few parts before I give the solution to all of you. Okay, so now let me discuss the solution with all of you. Let us begin with part A. I need to change my pen. So we will make use of the Fourier components to find out the cross-spectral density function W. So the Fourier component for the given field is given as the Fourier transform I'm just putting in the given expression for Vt. So these integrals give Dirac delta functions. That's because the Dirac delta function is defined as follows. So that's how we get these Dirac delta functions. Now the cross spectral density function is given as the expectation value of these Fourier components at the frequencies omega 1 and omega 2 in this manner. So let us make use of these Fourier components. This should be omega 1. So correct me if I make some calculational or some mistake in copying. Let me recheck once again. Okay, proceeding further. Now we are given that A and B are real numbers. So A star is nothing but A and B star would be equal to B because they are real numbers. Now I'll just open up, multiplying each term, all these brackets. That's the first cross term, then another cross term, Now since these a and b are real numbers, expectation is also the same, so that gives a squared delta omega 1 minus omega a. So all the expectations just give the same number. This completes part A. Now part B asks us to find out the intensity IT of the field. Intensity is given as expectation of V star V again. Since A and B are real numbers, A star equals A and B star equals B. That's intensity. Now let us look at part C. Part C is about finding the cross correlation function gamma T1 T2. So that is V star expectation of V star T1 V T2 pardon me. Now opening up the brackets, and since A star equals A and B star equals B, as A and B are real numbers, So this completes part C as well. Next is part D. Is the field stationary, at least in the wide sense? Now, a stationary process, we have seen this earlier in the first week itself, in the first or the second week. For a stationary process, all the correlation functions, which means the mean, the cross correlation function, the intensity, all these, and the higher order correlation functions, all these functions of the given random variable, all these correlation functions are independent of time. Time independent. Now, stationary in the wide sense, is a little bit more relaxed condition. So, relaxed meaning it just requires that the mean and two-time correlation function these two functions should be independent of time. So now let us look at the intensity. Why I am looking at the intensity? Because intensity is just the cross correlation function with both the arguments being same, and I just wrote down the intensity in part B. We will make use of that. Now clearly we see that this is time dependent because of the presence of t in the argument of the cosine function. So clearly this is time dependent. So this will not be equal to the intensity at time t equals to 0. So this clearly implies that the field is not wide sense stationary. And since it is not wide sense stationary, therefore it will not be stationary as well, because stationary process requires that it is wide sense stationary plus all the higher order correlation functions are also time independent. But here we see that the intensity is not time independent, which means that the gamma function, the cross correlation function, is not time independent. As a result, the field is not wide sense stationary. Now we move over to the last part of this question, which is to find out the degree of coherence function of the given field. So now let us look at the square of this function. Now these terms cancel out. V star T2 with this, V star T1, and even VT1 and VT2. So finally we get 1. So since the square is 1, that means the square root will also be 1. So the degree of coherence is 1 for the given field. This completes problem 2. So in the problem 2, we saw we were given a field and we calculated various aspects for the field: the cross spectral density function, the intensity, the cross correlation function, and the degree of coherence function, and even checked whether it is stationary or not, at least in the wide sense. So once again, take a few minutes to just understand what we have done over here, just to revise it once before proceeding to problem number 3, which will be the last problem for the day. Okay, so let us move to problem 3. There are 6 parts in this problem. Suppose the cross-spectral density function of a field is given by the following expression w omega 1 omega 2, and it comprises of a delta function and two spectral functions, where s plus minus is also given by a kind of a Gaussian spectrum, with the condition that delta omega is less than omega which is less than omega naught. The question is this field wide sense stationary in time? Then part B is plot the spectral density function as omega versus frequency omega, indicate omega naught, omega and delta omega on the plot. The above field, and then part C says of the above field enters a Mach-Zehnder interferometer with the time delays in the two arms being T1 and T2. Calculate the intensity I naught tau at an output port of the interferometer in terms of tau equals T2 minus T1, and we can assume K1 equals K2 equals K. Then part D asks us to plot the output intensity I naught tau as a function of tau and indicate omega naught, omega and delta omega on the plot. Part E, calculate the degree of coherence function and find out a reasonable estimate for the coherence time. And finally, part F, plot the degree of coherence as a function of tau and indicate the coherence time on the plot. So a similar question as earlier, in the sense that we are supposed to find out whether it is wide sense stationary or not, the degree of coherence and coherence time and intensities. So just read the question once again. There are a lot of parts involved in this question, so do not get confused with that. Just read it step by step and try to digest what the question is trying to ask. Okay, so let us now start solving. Part A. Due to the presence of this delta function over here, due to the presence the field is stationary random function, the stationary random process. Since it is stationary, therefore it will definitely be wide sense stationary as well, because every stationary field is wide sense stationary, but the reverse is not true. Every wide sense stationary field need not be stationary, because stationary requires time independence of all the correlation functions, whereas wide sense stationary requires time independence of only the mean and two-time correlation function. Now part B is to plot the spectral function. I'll try my best to plot spectral density function S omega. This is omega. This axis will be S omega. And let me try to plot. It will be like a doubly peaked Gaussian. And this midpoint is omega naught. This is omega naught plus omega. This peak location. This peak location is omega naught minus omega. Peak to peak distance is 2 omega, and the width of each of these peaks is 2 delta omega. Now let us look at Mathematica simulations for the same. If my drawing is too confusing, the Mathematica simulation will make it clearer. Let me open my Mathematica screen. The Mathematica programming environment. So I'm here in my Mathematica window. Sorry for those pop-ups. So this is the Mathematica programming environment, and we will use this to make plots. So the question is to plot the spectral density function versus omega. So this is what I have over here. So this is the spectral density function that I'm trying to plot. It is already there. Let me run it once again for you. So this is the plot for the spectral density function. The width of each of these peaks is 2 times delta omega. This central point is omega naught. This point where the peak lies, one of the peaks lie is omega naught plus omega, and the other point is omega naught minus omega. So maybe I can write here P1, P2 so that you come to know, although I've put the tick marks. So yeah, see this omega naught minus omega is where the first peak is there, and omega naught plus omega is where the second peak is there. And this x-axis is frequency omega, y-axis is the spectral density function. Maybe I can put in the labels. So omega, okay, I need to put s omega also. Okay, I'm sorry, some technical glitches. So there it is. Y-axis is s omega, x-axis is omega. Now I can change the values of these widths a little bit, and then you can see what happens. So right now, let me try and change the value of, first let us say omega. So instead of omega 10, let me put omega 50. See, the spacing between the two peaks increases. So omega controls the spacing between the two peaks. Now if I come back to 10, and let us now change delta omega. So instead of 1, if I change delta, oh sorry, this is because the width is too much and the spacing is not sufficient. Now see, so spacing is also increased and width also increases. If I keep the width 1, you see this, okay, this is the width. Now if I increase the width, see, it becomes broader. The peaks, width of the peaks increases. So this is how omega and delta omega control the spacing and the width. So narrower the width, sharper will be the peak. So that is for this plot. Let us get back to the next question. Okay, so coming back, Now we will look at part C, which asks us to find out the intensity at the output port of the Mach-Zehnder interferometer. So from the Wiener-Khinchin theorem, we have this. We saw the Wiener-Khinchin theorem earlier. Let me just show it once again. So this was the Wiener-Khinchin theorem, using which we find out the cross correlation function gamma from the spectral density function S. So I'm just putting in the expression for SW. Now let me make a substitution. Omega 1 equals omega naught plus omega, and omega 2 equals omega naught minus omega. This is the substitution I will make. Now I will make use of one of the results from the previous questions. This equation 1 is of importance to us. Why? Because it is the integral of this particular expression over here, and the integral of that expression gives us the following result. And if you notice that in the given question that we are solving currently, we have integral of this particular form, so we will make use of equation 1 to get the result. So making use of equation 1, I will write down the result directly. So to come at equation 1, we had done quite some substitutions and algebra, but right now I will not do all these like 6-7 steps. I will directly make use of equation 1 as a result. So this is coming from equation 1. Now let me simplify this exponential minus I omega 1 tau plus exponential minus I omega 2 tau. I'm writing now the real part and imaginary part separately. Now I'll use trigonometric results of cos A plus cos B. So that's 2 cos A plus B by 2 times cos A minus B by 2. Similarly, for sin A plus sin B, it is 2 okay wait so using trigonometry again, this will be 2 sin A plus B by 2 times cos A minus B by 2. Now omega 1 plus omega 2 equals 2 omega naught, and omega 1 minus omega 2 equals 2 omega. Just simplifying. So this gives me my cross correlation function as follows. Now I can write down the intensity at the Mach Zehnder interferometer output. This is time independent because it is a stationary process. Stationary because of the presence of delta function in the cross spectral density function. Thus, my intensity also, the value of this I0 is the following. It says 2. Why? Because when you put tau equals 0 in this expression, this exponential becomes 1, cos becomes 1, this exponential also becomes 1, you are left with 2. So, degree of coherence function is and the argument of this function is omega naught tau. Therefore, the final expression for intensity at the output port of the Mach-Zehnder interferometer will be the following. And also we are given K1 equals K2 equals K. So this is the final expression for intensity. Now, part D asks us to plot this final output intensity. So let us try to plot it. Something like this. And the envelope of this function is going to be this, joining the peaks, these peaks. So this axis is I naught tau, this axis is tau. Now the separation between these smallest peaks, this is related to omega naught. The separation between these peaks, which is connecting, which basically gives us the envelope, is omega, and the width of this envelope function this is the width of this envelope function. This is 1 over delta omega. So these are the three different kinds of widths over here. which come from these three terms in the expression for intensity. We have three different kinds of frequencies. So width of this exponential gives the width of the envelope function, this one. Width of this cosine function, cosine omega t, corresponds to this, and width for this cosine omega naught tau plus phi is over here. Now let us look at this in a much better way in Mathematica simulation. So we are back again in our Mathematica programming language for looking at the next question. Oh, sorry, not this one. So this question basically asks us to plot the intensity versus tau, intensity I naught tau versus tau. I naught tau is the output intensity of the Mach-Zehnder interferometer. So we have the expression for that, which is besides the scaling constant. The scaling constant is 4 mod k squared. So we are ignoring the scaling constant, it just scales the plot. So we have 1 plus cos omega t times an exponential, which is exponential minus tau squared delta omega squared by 2, and times cos omega naught t. We have taken phi k equals 0. So this is how the plot is. Output intensity of the Mach-Zehnder interferometer versus tau. And this plot is symmetric about y-axis. So for positive x and negative x, the values are same. This is because it is symmetric function. Cosine is a symmetric function, even function, exponential is an even function, and product of even functions is even. And you see, because of this 1 plus this term, therefore this plot does not go below the x-axis, below 0, because cosine can go from +1 to -1, but then we are adding 1 to it, so that as a result it gets shifted by 1, and this fluctuations you see are about y equals 1. Now since it is symmetric, we can actually just plot on the x-axis only, means only the positive x-axis. So here we are just looking at the positive x-axis, and this is the plot. Let me run it once again for you. So this is the plot. This is for the same values of omega and delta omega as above. So here it is omega is 10, delta omega is 1, and omega naught I've taken as 201. So let's say put it 100. So this is for the exact same values of omega naught, omega, and delta omega as shown in the above plot. Now let me change the values of omega naught, omega, delta omega and show to you what happens. So again, let me, instead of 100 omega naught, let me put 200 as omega naught. Let me increase the points. Okay, so this is, you see, the only difference between the top and the bottom plot is the difference in the value of omega naught. So if we increase omega naught, you see that these small fluctuations between each of these peaks increases. So you see that this is like an envelope is there. That envelope is due to the exponential function. That envelope remains same because I'm not changing the exponential function. Similarly, these broader peaks that you can see from my cursor, that is due to cosine omega t, and you see those also remain the same, these broader peaks, but the internal fluctuations between each of these broader peaks changes as a result of change in omega naught. Now let us try some more changes. Here you can see that I have kept omega naught as 100, which is same as this one. So as a result, you see that the peak to peak height of these smallest fluctuations is the same as over here. This smallest fluctuations peak to peak height that is controlled by omega naught, so that remains same because omega naught is 100 for this one also. If I run it again for you, see this, and delta omega is also the same, so this envelope function remains the same, but what we have changed is the value of this omega. So this omega is basically this broader peaks that you see, so that we have changed. So we have actually decreased it from 10 to 5. So if we are decreasing it, that's why this width is increasing. Some more example. So here I have changed the value of delta omega. So delta omega basically controls the envelope, and you see that if I decreased the value of delta omega, how this is changing the envelope function. So decreasing delta omega means that this envelope is becoming broader. So that is how all these parameters are changing. So let me just revise it for all of you. Let me make use of this plot over here. So let me just revise it for all of you. So this envelope function is an exponential function for this plot. If we just join it touches all these topmost peak points. So this envelope function is the exponential function. The width of this is governed by this delta omega. If delta omega is larger, then the width is smaller. If delta omega reduces, then the width increases of the envelope function. So that's the first width that we have over here. Second width is this peak to peak separation for these smallest peaks. So these the smallest peak to peak separation is controlled by this omega naught over here. Then you see that there is this kind of oscillating function which has a broader width. So this broader width oscillating function, uh, the period of that is controlled by this cosine function over here, omega. So this is omega. So periodicity of these smallest fluctuations controlled by omega naught, periodicity of these broader fluctuations controlled by omega, and the width of the envelope controlled by delta omega. So let us now get back to the next question. Coming back, we need to look at the degree of coherence function. Degree of coherence function, and then we need to find out the coherence time. So this we have already found out in the above part. Oh, sorry, in this question I have drawn the axis wrong. Since it is 1 plus this, so this will start from actually from 0. This is tau. Now coherence time is actually the width of this function, which is 1 over delta omega. Now if I make the plot, and the envelope will be this, joining all the peaks, and the width of this envelope function is 1 over delta omega, which is the coherence time. Part F is about plotting this, which we have already done, but let us look at the Mathematica simulation for better understanding. Mathematica simulation for this plot right here. So once again, we are here in this Mathematica programming language, and this time we want to plot the degree of coherence function. So this is the intensity function. For this particular intensity, we have this as the degree of coherence. So I have not taken modulus of this cosine over here. Let me take that modulus. So this is my degree of coherence function, or the mod of that. So mod of gamma tau versus tau. Degree of coherence function is gamma tau, and to find out the coherence time, we will plot mod of gamma tau, mod of the coherence function, and find out the width of that. So here also you can see that it is a product of two terms, this cosine term and this exponential term. So this cosine term basically controls the separation between these peaks, the fluctuations that are there, and this exponential term controls the overall envelope that is present. So let me plot the exponential also separately, then you will understand better. See this. I have up until now I was just talking about the envelope function and showing through my cursor or notes. Now I have plotted the envelope function also. So you see that this envelope function touches each of these peaks tangentially. So that's the envelope function, which is the exponential function, and the width of that is the coherence time. It is the width of the degree of coherence function. So that width is controlled by delta omega, and that width is basically 1 over delta omega. And once again, let me change the values of omega and delta omega and show what happens. let's see what are the original values. Omega is 10, delta omega equals 1. So omega 10, delta omega equals 1. This is the original. Now let me change these terms for you. Let's say I make delta omega also equals 10. So you see, if I increase delta omega, the width decreases of this envelope. So the coherence time also decreases. Now if I decrease delta omega, the width increases. As a result, the coherence time also increases. Now let me change the value of omega. If I decrease omega, you see that there are fewer fluctuations within this envelope. And if I increase omega, you see that there are more fluctuations. So if I compare it with 10, see this is with 10, and if I make it 20, you see that there are more fluctuations within this envelope function. So this was all about the coherence time and the degree of coherence function, and how we can actually find out the coherence time by finding out the width of the degree of coherence function. Notice that we cannot here take the width of the first peak. So if this is the first peak, you see, we cannot take the width of this first peak as the coherence time, because the function revives after going down to the minimum. After going down to 0, it revives once again, goes to a peak, then goes down to 0, then revives again. So this is an oscillating kind of function, but it has an overall width because of this exponential function. So this exponential function governs the overall envelope, and hence it controls the overall width. And that's how we can take the width of this exponential function as the coherence time. If So this brings us to the end of week 3. We looked at questions involving the Mach-Zehnder interferometer and the intensity at the output port of Mach-Zehnder interferometer, and also found the cross correlation functions and the degree of coherence functions. And the coherence time. So thank you very much. We will meet again next week.